There are some trends that we can predict based on the position of an element on the periodic table. The first one that we're going to look at is the atomic radius. And there's a couple different ways that we can measure atomic radius. One is van der Waals radius, where we cool the elements down until they form a solid and measure the distance between two adjacent nuclei. Another way that we can measure the atomic radius is by looking at it in different compounds and taking an average of the radii in those compounds. As you might expect, as we go down from one row to the next, so as we move down the group, our valence shells are getting further and further from the nucleus. Our effective nuclear charge is fairly close to one another, and we'll talk more about effective nuclear charge in a minute. So our atomic radius increases as we go down the periodic table. However, as we go from left to right, counterintuitively, it actually gets smaller. So as we add electrons going to the right, we are also adding protons. And because we're adding protons, there's a greater attraction for those electrons to the nucleus. And our atomic radius actually gets held tighter and tighter as we move further to the right on the periodic table, decreasing our radius. And so our atomic radius trend, as we go up the periodic table and to the right, our atomic radius actually decreases. The effective nuclear charge comes from something we call shielding. For example, we have an example of lithium, which has a +3 charge in the nucleus. Because there are core electrons, those core electrons shield the valence electron. So in lithium, we have two 1s electrons that are blocking the positive charge from the nucleus. And so our outermost electron feels a positive charge towards the nucleus of about a +1. So the core electrons shield our valence electrons. Based on our atomic radius trend, which do you think would be the larger atom? So if we have nitrogen and fluorine, which would be larger? Well, nitrogen would be larger because it is further to the left. If we look at carbon and germanium, which one would be larger? The germanium would be larger because it is further down the periodic table. If we look at nitrogen and aluminum, which would be larger? The aluminum would be larger because it is further left and down on the periodic table. How about aluminum and germanium? Well, it's difficult to tell in this case because we have opposing trends. One is further left and one is further down, and so it is difficult to tell which would be the larger atom in this instance. The trend for the atomic radius of transition metals is complicated just a little bit. If we look at the column of the periodic table, we do see what we would expect, that we are increasing in size as we go down the column because we're adding more and more electrons further from the nucleus. However, as we go across from left to right through our D block, the atomic size stays roughly the same. And the reason for this is because we have valence electrons in a higher energy level than the D block. So the effective nuclear charge on those valence electrons stays approximately the same because we're adding protons at the same time that we're adding electrons into our d orbital. When we form transition metal cations, we follow the same rule that we have forming other cations. However, we need to remember that the electrons, our valence electrons, are not the highest energy electron. We still remove it from the highest number first. However, we've added d electrons after our valence electrons because they're higher energy. After we remove those valence electrons, then we can start removing electrons from the d orbitals as well. So let's look at iron. Iron, when it is neutral, has 2 valence electrons. So they are written 4s2, 3d6, but this still is the highest number, which is 4. Those are going to be the electrons that are removed first. So when we form a cation of +2, those 4s electrons that get removed. If we form a +3 charge, then we start removing d electrons. So in the case of a +3 cation, we would remove one of the 3d electrons. This is part of the reason why transition metals frequently have a +2 charge. So let's practice. Let's write the electron configuration for zirconium and for the zirconium 3+ ion. Zirconium would start at krypton. We would then travel through the 5th energy level, 5s2, and we would go to 4d2 because zirconium is number 40. Now if we were making a +3 ion, we would remove the 5s electrons first and then start removing the d electrons. So our electron configuration would no longer have 5s electrons, and we would only have one 4d electron for the zirconium ion. How about the trends in our ionic radius? So for our ions in the same group we know have the same charge because they have the same number of valence electrons. As we go down the periodic table, we're adding more electrons further from the nucleus, and so our size increases. If we think about cations, we've lost our valence electrons and moved down into a smaller energy level, and so cations are smaller than the neutral atom because of the loss of the electron. Anions are larger than the neutral atom. The reason for this is because we have more negative charges being held on by less positive charges. We're adding electrons, making it more negative, which are going to repel each other for the same number of positive charges. So anions are larger, cations are smaller than the neutral atom. The interesting thing is that cations are smaller than almost any anion. So even our very biggest cations, they're about the same size as the smallest anions on the periodic table, which are fluorine and oxygen. If we have a larger positive charge, that means that we have less electrons for the number of protons in the nucleus, and so they're going to be pulled in towards the nucleus tighter. So the larger positive charge means that we have a smaller cation. This is for isoelectronic species. And isoelectronic means that if we have the same electron configuration, because everything wants to be like the noble gases, O2 minus, F minus, neon, sodium ion, and magnesium ion all have the exact same electron configuration. And so they're said to be isoelectronic. If we have a larger negative charge, our anion is going to get larger, and that's because we have less protons holding on to more electrons. So if we look at the radius, here are some cations, and it's pretty amazing how much we shrink. So if we look at neutral lithium, it's about 152 picometers. When we form the cation, we shrink down to 60 picometers. If we look at even our biggest cations, like rubidium, or 248 picometers, and it shrinks down to 148. So they do drastically decrease in size. We still follow the same overall trend of decreasing as we go up and to the right on the periodic table. If we look at our anions get larger because they're trying to hold on to more negatively charged electrons. So from our neutral atom, we actually gain in size. So we go for fluorine, we go from 72 picometers to 136 picometers. So they get larger. And we still follow the same general trend of decreasing in size as we go up and to the right. Let's choose the larger of each pair. What if we have sulfur or sulfide? Which one is going to be larger? The sulfide ion is going to be larger because it has more electrons with the same number of protons to hold on to those electrons. The anion is going to be larger. What if we have calcium or our calcium ion? Which will be larger? The neutral calcium will be larger because we've lost electrons from the outermost shell to form the calcium ion. So our cations are always smaller than our neutral. What about bromine and krypton? Well, bromine is larger because it has fewer protons but the same number of electrons. The protons cannot hold on to the electrons as effectively, and so our anion is going to be larger than krypton. This is an isoelectronic species. Here's a practice for you. Pause the video to see if you can put the ions in order from smallest to largest. If we look at our first example, titanium is higher on the periodic table, so it will be smaller than zirconium. And hafnium is further down the periodic table yet, and so it will be the largest. If we look at sodium, magnesium, fluorine, and neon, these are isoelectronic, so the larger the positive charge, the smaller the ion. So these get put in order from largest positive charge to largest negative charge. If we look at the last four, these move around the periodic table a little bit more, but our gallium has the largest positive charge, then our indium. Then if we look at bromine and iodine, bromine is higher on the periodic table, so it will be a little bit smaller than our iodine, which is further down.